Okay, good morning, students. Today is August 25th. This is the session previous to the last. Tomorrow will be the last session. Okay? And today we're going to complete the example that we were reviewing last session. Then we're going to describe the analysis of the transverse strength of the ship hull, just to describe, because we don't have the time to introduce a technique to analyze this type of analysis of frames. And then probably we will start reviewing. It's like I wouldn't say a summary, but this is just like highlighting the main points in a chapter on design, called structural design, from one classification society. Okay, and the idea behind that, or the objective behind that, is that you get familiarized with the terminology that this type of information brings from the classification society. It's interesting that you start seeing the relationship between what we studied here in class, okay, in a very analytical, strict way, and the way the classification societies have converted those equations, okay, from the structural mechanics into very practical relations to design the structure of a ship. Okay, that's a general idea. Okay. So we will go over on that until tomorrow. More or less, that's the agenda for these last two sessions. Okay. So let's see if we can share this screen. You see, can you see my full screen, people? Can you see my full screen? Sample? Anybody? Could you please confirm? Okay, so you can see my screen. Okay, so let me see. Stand here. Yes. Okay, so we are going to apply just a simple procedure in order to analyze this structure. Okay, this is an analysis of the tanker ship. Okay, this is a real ship. I had to analyze it some years ago.
Doctor, yep. There is not full screen yet.
Not full screen. Supposed to be full screen now. Let me put it in here and see if I can. How about now? Isaac?
Now it's correct.
Okay, thank you very much. Thank you. That's your job. That's your job, to correct me. Okay, so these are the main dimensions of this ship, and it's every time you see these, okay, try to see if they make sense or not. Okay. For example, there's the usual ratio between beam, okay, and depth. Okay. For example, in a small fishing vessel, right, length over beam is usually about 4.5 or something like that. Okay, in this case, you see that these two, okay, the relationship is about 6. Okay, maybe a little more than 6, right? That's because this is a kind of large ship for our numbers. Okay. Usually, also B over D is about 2. That's about this. Okay, it's a little bit more than 2. Okay. thing which is very important is the difference between these two. Okay. Report, and what I ask you to do is try to start seeing these numbers, not just a figure there, but physically, this is what you mean. Okay, 65 centimeters, that's not much. Okay, so you have a small roll angle and you have water on deck. The problem with this is that, or the reason for that is that the cargo is so large, okay, that the inertia is so high that they don't move much, okay? Yeah, since the load is there, the cargo is there, the kg is relatively low. So still the GM in the loaded condition, it's a good one, okay? In the light condition, and something also very interesting, okay, you see here that this number is very small compared with this one, okay? And you see that also this is the trim is very large. So in the light condition, usually in a tanker vessel, right, basically the forefoot is basically just touching the water. You even have negative draft on the forward end in the light condition in a tanker ship. Okay, because there is no cargo at all, right? So they just like that. Okay, and in that condition, okay, LCB is not equal to LCG. Remember that this LCB and LCG are usually expressed in a axis which points parallel to the baseline. And when you are inclined, okay, the baseline is like that, and the horizontal is like that. So equilibrium means that the weight is here and the buoyancy center is here. But the distance in the x direction, they do not coincide. So be careful when you have to do a stability analysis of this type of ships. Okay, so this is the, sorry, I missed one, transparency. No, we're fine. Okay, this is the one. So this is the general distribution of the ship, okay? It has double bottom, but not double hull, okay? So on the sides, you have no double hull, double side. You have double bottom, not double side. This is something that I have to insist, okay? This figure on the left, okay, people, please be careful. Okay, this figure, and at the beginning of this chapter, I presented this part here also. This is part version A and version B of this same figure. The terminology in these figures, you are responsible for that for the final evaluation. Okay, I still don't know how I'm going to evaluate you, but I'm going to. Okay, so please review this. Okay, so you learn the names, the terminology to describe each one of the elements in a structure of the ship. Okay, and in this on the side, this is the copy, not a good one, a copy of the plan, right, of this ship. And you see that there is a lot here, down here, of similarity with this one. This is from a textbook, and this is in the real world. Very important to recognize this intercostal side girder here, and here you. The distance from here to here is 2.5, which is a classical number that classification society employ. Okay, so you have, even though this is a longitudinally framed system, right? So you need these little longitudinals. See, every 2.5 meters, in this case D and V, have to include this longitudinal side girder. Okay, go to the next one, but then you have the lateral reinforcement, lateral frame. So you don't need another side girder. if you had more than 6 or 7 meters in beam, probably you need one and then another side girder, and then you go to the side of the ship. Okay, not in this case, since we're just above 5 for the half beam. Okay, so all of that, and let's do this analysis. So here we have the main structure, okay? So we have the spacings. In this case, the distance between two bulkheads, you can read here, it's 10.8, okay? That's distance from here to here, it's 10.8. So you get probably 1, 2, 3, 4 spaces. That's about 40-something meters. You get it, maybe 20 here, that's 60, and you got 10 more here, so that's your 70 meters long. So all of this has to make some sense, okay? Now, what else? Here, you got the spacing between the center and the side girder, 2.5. So if you include 3 longitudinal, the spacing is going to be 0.625. In this case, I'm just writing in the plan 0.63, okay? Height of the double bottom, 0.85, that's a typical number. This is a 75-meter long ship. That's typical. And these properties, remember, this is something that you have to keep in your mind. So this is the calculation of the required section moduli, okay? In this case, we calculate the bending moment in still water. So that's the first thing that we do. So this is still water. Okay, and we remember that the distribution assumed by the classification society is about this, more or less. Okay, so this value here in the central part is this one here that we have got. See, this is something very interesting, right? Because you see this formulation, you don't need to get the distribution of the weight, the distribution of the buoyancy, and all of that. You simply apply this formulation because that's the experience of the classification society, right? Now the second line, the third line, this is the an estimation bending moment in waves. Okay, so here we have hogging, we have here for sagging, we have these two numbers. So here we have to be careful. Remember that for hogging, okay, this is hogging. Okay, so the deflection is going to be like that. So usually we take this as positive bending moment, okay? And usually that's the sign of the still water. Now, if you apply, this is for ships of length less than 100 meters, okay? If you go to the regulations for ships with length larger than 100 meters, then here and here you have a sign, because as this is a comment that we made in one of the previous classes, is that when you increase the length of the ship, okay, there is more and more importance on this primary behavior, okay? So that's why we need this, be a bit more careful with these signs. In this case, in general, the sagging, has different sign. This and that. Okay. So in sagging, this is negative. Hogging, this is positive. And in this case, this value is also positive. So to calculate this, what we do is we sum up this 30,000 with this 29,000 and do this operation. And this is the result that we obtain. So that means that in water, in waves, okay, we need this sectional modulus for the whole section of the hull, right? And if you employ number of section modulus, then the stress on the deck will be 175 exactly, okay? But the regulation says that we also have to calculate this value. And it says that the section modulus cannot be less than this one. My interpretation of the rule is that this is the accidental limit state. This is the operational limit state. Okay, and you as a designer, you have to consider both situations, right? Okay, so in this case, the accident, let's suppose that this is correct, right? So that means that in the accidental limit state, you need to satisfy this value. So you have to have, since this is larger than that, you have to satisfy this requirement. Okay, so to check this requirement, what we need is basically the thickness of the section, of the plating of the section. So we need to calculate the thickness on the deck, on the side, bulkhead, double bottom, and bottom. Okay, that's the next step. Okay, so to calculate thicknesses, we need pressure. Okay, so this is a summary of the estimation of the pressure in each part of the structure, of the section. Okay, so we go here, some pressure. Here, we have a lot of pressure. Here, we also have a lot of pressure. Here, we have also some pressure. So we need to calculate all of these in order to calculate the thickness. Now here, this is the floors or the longitudinal girders. The thing is that these elements, okay, I'm going to try to draw a double bottom, right? So the double bottom will be something like this. This is the floor. So this is a side girder. Okay, now what happens is that this is the plate. So in this case, let's suppose that the double bottom is filled with water. In this case, there's going to be some pressure acting on these elements. Okay, so the pressure will be acting like this, and will be acting because these floors and these side girders, it is in the distribution. Let me go back to the distribution of the ship. Here, you see that this is a tank in the double bottom. That means that this longitudinal here, okay, will suffer from pressure acting in this direction. And similarly, this floor will support pressure acting in the axial direction. So these vertical plates, which are the floor and the longitudinal girder, they suffer a perpendicular. You have to design those elements to support it. Okay. So these are the values that we see here at the end of this table, right? So hopefully this is useful to you. And this is the formula that was employed to calculate each one of the pressures on each one of these sides. And then with the pressure, we can go on and calculate the thicknesses, okay? And in this case, I'm just going to explain this. The other are similar. For example, for the bottom, this is the pressure that we need to apply and the formula that we employed, okay? This is the aspect ratio of each plate panel, right? So this is going to be equal to the spacing between longitudinals and the spacing between transverse frames. So it's going to be 2.7 divided by 0.63, more or less. Okay, that. With this aspect ratio, we use the Timoshenko solution, and so we get the beta value for a clamped plate evaluated at the center, and this is the value that we obtain. Remember that this is a discussion that the two class sessions ago, and we said that when we have a plate in different stiffeners, right, the model to analyze this is not an all clamped plate, because the stiffeners, they have to rotate a little bit, and when they rotate a little bit, the boundary condition is not clamped anymore. So this causes a redistribution, and more or less, the bending moment on the side and the bending moment at the center of the plate are the same. So in this case, that's what we are doing. This B alpha is just a value which corresponds to the ratio between the stress, allowable stress, working stress from the classification rules, and divided by 235, which is the standard yield value for the stress of the steel. Okay, so they recommend to have a 120, okay, 120 for the working stress, and that represents 51% of yield point. Okay, with all of these values, we can evaluate the bending moment. Okay, with the bending moment, we apply this formulation. This is our analysis, and this is the required thickness only for the structural part. We have not added any corrosion addition. Okay, and if we apply, this is the formula from DNV. This is something that we discussed. Okay, you combine all of these terms and these unit conversions, and the result is this formula. By this formula, this is the result. Basically, they are the same. Now, remember, similarly as in the previous calculation for the section modulus, for the thickness, they also consider, my interpretation is this value, 6.73. That's the required thickness considering operation state. Okay, so the ship is moving in the water, so the total pressure acts, and if you put 6.73 for the thickness, the plating is able to support the pressure that you expect when working in this condition. But, for example, you take the ship into the dry dock, and when it's sitting dock, okay, it is possible that the limits of the block points, for example, in the center of the plate. That exerts a different loading. So that's, for me, that's an accidental limit state. Okay, and they have accumulated formula that considers that situation. That's a very strong, very, for example, we could do something like that, right? We could say, okay, let's suppose that we have a concentrated force in this plate, okay? How much is the concentrated force? Well, what we can do is we can say, okay, we have a total displacement in light condition, and we consider a percentage of that as the force in this plate. And then from that, we could go on and try to determine this expression, but that's just too much. Okay, so this is the result. So in both cases, operational or accidental, the ship has to sustain its integrity. So what we have to do, okay, take the larger value. So we have to include this value here, 7.88. And to that, a summary of that is here. Okay, so I was mentioning 7.88. That's for the thickness in the bottom. And in the bottom, this is the bottom, they finally put, this number is taken from the plan. 9 millimeters. Okay, so they have added just a little bit about 1 millimeter. Okay. And similarly for the other elements. Okay. So we know this calculation. This is the position of the centroid. Okay. So let me go back just a little bit. I need the depth. The depth is 535. 535. Okay, so from here to here, it's 235, right? 535. Half of that, it's 2.6 or something like that. So this is less than that. Okay, meaning that here I have bottom and double bottom. So we can expect to have the neutral axis below that. Okay, so if we have 5 point something, so the half of that is going to be 2.6, we should expect this number to be below that. Okay. In one of the exams, one of the quizzes, I gave you a symmetric section. Okay, so immediately you knew that this is something you should do. You see a symmetric section, the same flange in the top, in the bottom. Immediately, the neutral axis is in half of the height. People did this calculation, and at the end, it didn't coincide. But you're not analyzing results. Okay, so when you calculate this, at least do that check. Okay, include a line. Okay, let me draw it here. So here, let's suppose that more or less here we have, this is d over 2. And you see that this number is below that. Okay, so that's fine. So this is our axis. So makes sense because you have more material in the bottom than in the deck. And from that point, you can expect that the section modulus here in the deck. So this is in the deck. In the deck is lower than in the bottom because the distance is larger. So this is the value that I have to check, because if we take this is going to be much larger than this one here. And you see that this is what? Maybe 5 or 6% larger than this one. It's very, very, very interesting, right? I did this calculation. I have an Excel table and change this. Okay, the deck plating thickness. And I changed it to 7.5 millimeters. And in that case, this value was below that one. So my impression is that they did a very good job, right, in trying to get these plates and then increasing so that we could satisfy this requirement. Okay, since we are increasing from the previous table, we are including a little bit more material than the required for the tertiary stress, but just a little bit. Okay, so that's that. So we are, with this situation, we satisfy this requirement. Okay, now in this case, we did not include the longitudinals. So that means that it's going to increase a little bit this inertia, but I don't expect the increment to be that large. Okay, so that's going to be some increment, but I don't expect that to be that large. Okay, so it's a good idea for you to do this calculation. Okay, include just the plating, then include the and check in what percentage does the longitudinal contribute to the bending stiffness of the ship hull. That's a good number to have in your mind. But anyway, so let's go to analyze the floors. And as I said before, we have these vertical plates limiting the tanks, so they support a pressure, and we have to have enough thickness to support it. So that's what we do here. So this is the longitudinal, this is This is longitudinal, and this is the floor. So this is the aspect ratio. And with that, we do something similar with the plating for the bottom, okay? So we have an aspect ratio, plate aspect ratio. We take this value from Timoshenko and the center of the plate. We explain that. This is the permissible value from the classification society rules. And from that, we calculate the stress, the thickness, okay? This is the formulation application, the result of applying the formulation from DNV. So this is very close. And here, again, we have to calculate the limit state, considering operational and also considering accidental. And in this case, the operational is larger. So that's why we take 8.1. And to that, we have to add a little bit for the corrosion allowance. All of that. Then we go to longitudinals. I'm sorry. In the case of longitudinal, okay, we can consider that they are, in a simple way, they are like a beam. They are a beam clamped in each one of the transverses, because this is longitudinal framing system. Okay, so the longitudinals are smaller, and they are being supported by the transverse. Okay, so if we assume that the stiffener completely is supported completely by the transverse, this is reliable assumption, because this is double bottom. So basically the height, okay, this is a transverse, its height is 85 centimeters. So if you consider the height of a beam, 85 centimeters in height, the stiffness of that is tremendous. So I think that this assumption is quite useful, and that's why you see it here. Okay, so this is a formulation from DNV. In this case, you take 2.7 as the span, unsupported span of the beam, and then we do this calculation. In this case, we take the effective 100 effective plating for the breadth. Okay, so that's the from here to here. Okay, so as we see it here, the complete spacing between the stiffeners is effective. And we do this calculation to check the available section modulus. And yeah, we have to be careful, because the minimum section modulus is on the flange, not on the plate. Now we have to be careful, people, because in the last part of this session, or this part, we're going to combine the stress, but in this point in the plate. Right now, I have to consider that on the flange, okay, occurs the largest stresses on this section. Why? Because this distance from the plate to the neutral axis is very small. It's 2.85 or 86 centimeters. It's about this. While the height of this web is 15 centimeters, like that. So that these details, they have to be in your mind. And then, okay, so the last step that we're going to take is to do a combination of stresses. Okay, now here, the animation included a fake. I'm sorry. So this is a simplified version of the structure. Okay, this is the floor. This is another floor. Okay, this is the side girder, and this is for example, the longitudinal bulkhead. Okay, so from here to here, this is 0.625 meters. From here to here, that's 2.7. From here to here, it's 2.5. I just draw two longitudinals. I should have drawn three, but I mean, okay, now, this is the point where we want to combine. Why? Because in this point, okay, the stress in this direction, the tertiary, okay, if we are not, okay, you can consider that the curvature in this and this edge is 0. Okay, so in here, okay, the tertiary deflection, it's much larger. So the deflection is going to be like that. The deflection here is going to be like this. So here, the bending moment is going to be larger than in here. So that's why we selected this point. Now, in these cases, when you have to do this analysis, the typical situation is that try to do this analysis in several points, just to check that your intuition makes some sense. Okay, so calculate also, and then compare. Calculate the von Mises equivalent stress and compare in each one of the points, and check if that makes some sense or not. Okay, so so here, I'm sorry, I should have included the directions. Okay, X, this is Y, and this is Z. Okay, so in the X direction, we have the primary stress. So this is the primary stress. Okay, so primary stress, we calculate it as with the bending moment divided by the inertia. Now, in section modulus. But in this case, we have to be careful because we are calculating this stress in the bottom. Okay, so let me go back. Here, okay, I have a double bot. I'm sorry, a section modulus on the deck, and this is less than this one here. So that's why we compare this with the required. But if we are calculating in the bottom, this is the sectional inertia that we have to, sectional modulus that we have to calculate, to use in the calculation. Okay, so you can do this check. Okay, you can do this check, and the Classification Society says that when you want to do this local stress analysis, you have to take the wave bending moment and divide it by 1.7, right? Because they usually do not occur simultaneously, the maximum value. So that's why. Remember that the bending moment in waves, it's a quantity which is changing in time, right? So that means that not necessarily the three effects take the largest value simultaneously. So if you take the complete value, you're going to it's a structure, analyze a structure with an extra value. So this is the result. This is the result. So it's only 55 megapascals as the primary. So this is the in the bottom. In the bottom. Remember, every time you calculate these things, okay, even though this is just one component, it's a good idea to compare it with 235. Then we go to calculate the secondary. Now, since this is the beam, okay, the normal stress because of the bending of this beam occurs in the X direction. Okay, now let me draw here the deflection This is the deflection of the longitudinal. Okay, so in this area where we are calculating, in the plate, there is going to be some compressive stresses. Okay, so we have to be careful. And for this, okay, we have to consider the section modulus on the plate. So let me go back here. Okay, we have this number. This is the number for the section modulus on the flange. And this is very close to the required value. Yeah, but we are calculating the stress, the secondary stress, not on the flange, but on the plate. So this is the value for the sectional modulus that we have to consider. Okay, this value here. And we put it in here. So it's going to be minus 15 in compression. So this is compression and this is compression. You see this value? Very small. But remember, this is in the plate. On the flange is very close to 160, which is the allowable value. But we are analyzing down here. Okay. For example, we could analyze, it would be a good idea for you to do in the flange. In the flange, you will have a longitudinal, and also you will have this stress. So the two will be combined. But there will be no tertiary stress. Now, the tertiary, okay, the tertiary, remember that the largest bending moment occurs in the direction of the shortest side. So obviously, this is the direction of the shortest side, but this is the y direction. So that's the tertiary points in the y direction. And this is the way it is calculated. A depends on the aspect ratio. This is similar to Timoshenko solution. This is the pressure that we have on the bottom. B over T, B is the shortest dimension, and T, of course, is the thickness. We evaluate that to 170. We have to be careful because both are possible. Because remember, in the thickness, on one surface, on one face, the stress will be positive, then in the other will be the same value with both negative. So I'm using both values here just to see the worst situation. Once you have these three values, we can combine them in the von Mises expression. Okay, this is von Mises, and this is the result. So in this case, I'm taking the negative value for the tertiary. So if I use the negative value, then we could obtain a combination. No, I'm sorry, the positive. The positive. If I take the positive, then in the other direction, they are negative. So yeah, as a result, you're going to add. And you have this value. This is kilograms per centimeter squared. Janos, how much is this in megapascals? Janos, how much is this in megapascals? You there? No? Janos, are you there, please? No? Mr. Ramirez, are you there? Would you please turn on your cameras, people?
Good morning, doctor.
Hello. How much is this in megapascals? How much is this in megapascals? You can do it because, come on, this is the full semester. This is something that we need to do every time. We need to interchange units. It's so important. Mr. Cedeño, please help me. Don't tell me you can do this. Come on. You should do it so easily. Come on, convert units. If you cannot convert, I don't think you should deserve to be called an engineer. Come on.
221.92.
To what? 231.8. So
No,
it's basically
221.9.
221. Okay. So you multiply this by 9.8, 9.81 and divide by 100. So it's
Yeah.
about just very close to dividing by 10. So it's 220. So, but the thing is that this is very close to 235. Very. So they have done a good design. Okay, they are not wasting any material. That's the final message here, right? So it's see, and this is a ship that has been operating. Well, it was operating for many years. It was built in Japan. People, is there any questions about this process? People, any questions about this process? No? Okay. Okay, so that's the first point of the agenda. Let's go now to the second point. So this changes. That's it. Okay, now let's go to secondary. You see my full screen, people? Can you see my full screen?
Yes, doctor.
Okay, so this is the last point of this chapter. And as you see here, it's just an estimation, it's just a description, okay? We need basic relations, but usually there are some specific methods that we can employ. And including, we can include that the final will be presented next semester. Okay. So let's do it. So this is a typical structure of a ship, and we can recognize these elements. This is the frame, transverse frame, okay? Sorry. On the bottom, on the side, and on the deck, okay? And we see that the pressure now is acting in this direction, okay? Okay, so it's like, let's define this plane, the X plane, and you see that the loads, the forces are acting in the plane XY, okay? It's different from, for example, plate bending. In plate bending, we have a flat plate and the pressure was acting in the transverse direction. In this case, we have a plane like this, and in this plane, we have the loading acting on the structure, on the transverse frame. Okay, so that's the analysis that we want to do. If we do not include enough strength, there's going to be deformation in this direction. Okay? Well, we don't want that. Okay? So, this is a comment taken from I forgot the name. My favorite book, Strength of Ship Structure, from Mukle. Please help me reading this, Ms. Arechua. Would you please help me reading this?
Yes, doctor. Strokes A, B, C, and oh no.
Analysis.
Consider a complete ring around the ship. For example, in a transversely framed ship, a combination of beam, floor, and side frame as a plane frame group of beams with loads in the plane of the system.
Okay, so they recommend to consider this as a complete ring. So it's like going like this, all of this, and close it. Okay, so include if this were a transversely framed shape, okay, is that this spacing is very small. So each one of them will have a beam, okay, that's here, this deck beam, floor, that's on the bottom, and on the side. So you will have a complete ring. And you have the pressure and the weights, probably, for example, on the deck, you have some weights. Also, it is possible that below the main deck, you have the cargo. So the cargo will exert some force downwards, okay? And then this group of beams, they have to be analyzed, okay? For example, this is the model that they recommend, okay? So it's like a full ring. Now, in this case, we see that we are only analyzing half of this, okay? So what we can do is we can take advantage of the symmetry, okay? So we see that if we, on the right-hand side, okay, we have the same geometry and the same loading that on the left, then we could set up some parameters so that the analysis of one half of the structure thinks that there is an extra on the right-hand side, even though we are not including in our calculations. What would be the conditions to consider symmetry in this part here? So let's suppose, let me include here. See, for example, let's suppose that this is, for example, like in this case, this is, no, let me see, this is Y and this is Z. What would be the conditions here in order to have symmetry analysis? For example, I have no, but I'm talking about bending here. So remember that tau equal to 0, that means that you're analyzing the plating. In this case, it's of the frame. So let's suppose that I have a force here. For example, I put, I don't know, a welding machine on the left and also another welding machine on the right. So we have a symmetric loading. What would be the type of deformation profile? And from that, what would be the conditions in here? Anybody? What would be the deflection of the deck beam? If I have a force here and a similar force here, what would be the conditions to be applied here in order to analyze only half and taking advantage of the symmetry?
The slope is 0.
Exactly, the slope is 0 because you're going to have something like, let me change color. Let's go green. Okay, so the deflection will be like this, that. So here, you could deflect vertically, but no rotation because you have the same on both sides. Also, the shear force will be 0. There you have it. So you have only half of the structure, apply conditions here and downwards also, and then you don't need to include both sides. If you have non-symmetric loading, then you have to analyze the whole thing. That's all. Okay, now, to analyze these things, there are some processes, and we don't have the time to explain them, so I'm not going to bug you with that. But in the next semester, in final elements, okay, we can analyze this plane frame, okay? This is an example that we could include in our class. Isaac, usually we use the pitch, remember?
Yeah.
Okay, let's do a promise to all of you people who are coming next semester for finite elements. We promise you that instead of a bridge, as an example, in the last part of the class in finite elements, we are going to include this transverse frame structure. Okay, we promise you. And by now, because we don't have the time. Okay, now let's do some details of that. Mr. Ortega, would you please read this for me?
Yes, doctor. A section of the structure having a length equal to one frame space will be.
Okay, just a second. So, in the axial direction, we consider one frame space. Okay, let me draw here. So this, oh man, I didn't select. So this is the frame space from here to here. This is S. Okay, so in here in this frame system, it's like having this. So this plating has to be considered when you calculate the inertia. Okay, so I have the plating and the reinforcement. The transfer is shortened in this case. So probably it's an angle, so you have a little web and a little flange. So this combination, okay, has an inertia and a section modulus, and you go on. Okay, please, Mr. Ortega, please go on.
Okay, and equal to one frame space will be in equilibrium under the forces of its weight and the weight of all cargo, etc., which is carries and the force of buoyancy.
Okay, so we do this analysis, okay, and then we consider the forces. So we have the force from the pressure. We have weights. Maybe we have another weight here. Okay. All of this has to be in equilibrium. Okay, that's more or less the premise that we could follow. Okay, so we take every frame, and every frame with the corresponding loads, there has to be an equilibrium in the plane, in the YZ plane. So we have the pressure. Remember that on the side, the pressure is mainly transverse. In the bottom, pressure is mainly in the vertical direction. So we have to be careful with these directions. On the deck, probably there are going to be some concentrated forces because of the weights, winch, anchors, things like that. In the bottom, it's possible that you have distributed load because of the weight of the cargo. This has to be in equilibrium. That's the an assumption, a hypothesis employed in order to analyze each one of these frames. Thank you. Okay, let's go on. I'm going to give you this. This is basically a transverse frame. In this case, of course, this is not a ship. This is a round structure, right? So it's a warehouse. We have a lot of space, or a coliseum. Okay, tell me, what do we mean? What do you understand by this? What does this mean? Ms. Valdez, what does this mean to you?
A simple support.
A simple support. And in boundary conditions, what does that tell you?
Deflection is 0 and bending moment is 0.
Exactly. So this point cannot move in the direction. In this case, it would be V. In the W is also going to be 0. I'm sorry. Jesus Christ. But also, it can rotate freely. See, because the point is here, but it can do this with no opposition from the foundation. So as you said, the bending moment is going to be 0. So in this case, M, where am I? This case would be M sub X In this point, it's going to be 0. So these are the conditions. And this is a distribution that of bending moment. And as Miss Valdez said, you can see that in this point, okay, there is no bending moment. And from that point, increases linearly up to here, because this increment, remember, is due to the fact that there is no motion in this direction. So there's going to be a shear force in the y direction in this point. If you have a shear force, a certain shear force here, and there is no loading, dm dx is equal to minus v. So since v is a constant, then the bending moment changes linearly. And that's what we're seeing here. Then in this point here, the bending moment in the vertical element is equal to the bending moment in the horizontal element in this point, because they are like that. So the bending moment here is transmitted to the other side, to the other element. So you see that this value here is equal to this value here. Now, after knowing this value of the bending moment, you start changing. It's like considering this as a beam. But in this beam, you have loading, uniform loading. So in this case, you integrate that, and you will get you integrate twice to get the bending moment, and so you have a quadratic variation. Again, in this point, the bending moment is the same in this point for this element than for that element. So you have this value, and then you have a change in deflection and distribution. And on the other side, you have similar behavior. Okay. Now, what's the difference of this with respect to that, Mr. Waman? What's the difference between this and that, Mr. Waman? Please answer me.
That is clamped.
Exactly. So it is clamped. So the deflection is 0, but also the slope is 0. So if we start here, the deflection will be like this. And you go in this direction. But here, there is no slope. So in this case, if this leg tries to rotate in this direction, the bending moment, the bending effect generated by the foundation prevents that and generates a moment and brings it back. So you start vertically, and then you can deflect to one or the other side or the other. But here, there is no rotation. In order to avoid having rotation, then you generate a bending moment here. So yeah, you're right. That's going to be the larger difference with the other case. That's what we have. And you see immediately that in this case, immediately that here, as different than here, okay, the bending moment is different than 0. In here, so dmdz, dmdz is equal to a constant. If you integrate that, then the bending moment will vary linearly up to here. And then you have a quadratic variation because of this double integration of this constant. And on the right-hand side is symmetric to the other side. Okay. Before we go to the break, this is the case, okay, of the structure of a ship. Okay, we have simple structure. So we have a deck frame, side, and we have a floor. And here we have a vertical reinforcement in the longitudinal bulkhead. Okay, let's suppose that we have a longitudinal bulkhead. So we have a vertical reinforcement to that. Okay, so we have deck frame, side frame, floor, and the reinforcement of the longitudinal bulkhead. That's the frame that we want to analyze. And this is the distribution of bending moment. Okay. Symmetry here, there is no rotation, so we have a bending moment. Similar here. Now here, okay, there is some change in bending moment, and then in this point, they have to be in equilibrium. So we have a moment from the vertical element, a moment from this side, and another moment from the internal part. So the three of them have, so this point is in equilibrium. It's different than in this case. It's the same as this one, because there is only two. And then you have a variation. Why you have a variation here? It's quadratic, because on the side, there is some pressure. Here, there's no loading on the side. So you have a linear variation of bending moment. Here, you have a loading on the side because of the pressure from the water. So that's why you have a quadratic variation. So this is a nice analysis that we could develop next semester. It's taken from this reference, Naples, Italy. And this is a hypothesis. They assume this. Mr. Villalba, would you please read the hypothesis, please?
Yes, hypothesis. Frame with prismatic beams, not considering the ends bracket.
Just a second. Prismatic beam. What do you mean by prismatic, Mr. Villalba? What do you mean by prismatic?
The same along the
It's a constant section, yes. So that means that from here to here, the inertia is the same. From here to here, the inertia is the same, etc. And what they say is that they do not consider the end bracket. Okay, so in the connection between the deck frame and the side frame, you usually include a bracket. So let's consider that the bracket does not participate in the inertia, but they could consider because the bending moment in this element, in this point here, is equal to the bending moment of the vertical element at this point here. That's because of the action of the bracket that does this. So the same rotation in the deck frame occurs on the bottom. Okay, go on, please, Mr. Villalba.
constrained with a simple bridge and with double pendulums on the diameter plane.
Okay, so here they're considered as simply supported. Usually, the thing is that, for example, you have a very strong floor. That means that in this point, you could consider this is clamped for the side. Double pendulums on the diametral plane. That means that here and here, there is some symmetry. Okay? So that means that they can move in this direction, but they cannot move in this direction, and that they cannot rotate. Okay, so that's the assumptions, and these assumptions can be converted into boundary conditions, and we could develop this analysis. But remember that we have one beam here and another beam here, so they are different. Now, the deflection in this point is the same, but the deflection is in the Y and in the Z direction. So we have to be more careful with the analysis. So that's why it takes longer time, but we don't have the time to explain how we can solve this. Conclusions, that's what they found. Let's hear from somebody else. Mr. Benavides, would you please read the conclusions that they reached? People, would you please turn on your cameras? I want to see. This is basically well, we still have one more session, but I would like to know you. I don't see. I walk by the street and see anybody and any of you, and believe me, it's difficult for me. So that's why. Okay, please, who else? Mr. Benavides, would you please read the conclusions?
Okay. The more realistic external constraints are a simple support at the bilge,
So here, this is the village. Even though they started considering, well, they assume a simple support in here. So they're saying that this assumption is adequate. Go on.
A spring with vertical stiffness at the longitudinal bulkhead.
Here. So instead of this, include just one spring. Okay?
And a double pendulums at the nodes on the diametral plane.
Here and here. So this point here cannot move in this direction, only move in this direction, and cannot rotate. Similarly for this one. So use that here and here in, and this point considered as simple support. These are the best assumptions to analyze this. That's what they found in this. So we can follow these recommendations, and we could try to do this with the final element method next semester. And we can, at the end, we can obtain and compare the resulting bending moment distribution. Okay, that's a promise. Okay, this is recorded, so Isaac, you have a compromise with these people.
Okay.
And me and you. Write it down somewhere so we don't forget. Okay, so this is something that we have to do. Okay, so we have this element, they are connected, and similarly in the bottom, you have a bottom frame, it's connected. So all of these, they are frames which are connected. And of course, that's brings a degree of difficulty. What we can do, we can simplify. We can simplify. Now, let's suppose that, for example, the side, we consider this element, okay, you see that this is stronger than this one here. That means that we can assume that the rotation of this element is very small. So if this is that, what we can do is we can consider this frame as clamped on one side. Now here, it is possible that since we have symmetry, okay, we apply a load here and a same load on the other side, okay, we could allow this point to move in the vertical direction, okay, can move like this, but cannot rotate. How do you call this support, this type of support? How do you call this type of support, people? Mr. John Romero, Jandri, how do you call this type of support? Can move, but cannot rotate. This is solid mechanics. Pardon me?
Guided?
Guided, yes, this is guided. So this is just a simplification. So you just take one piece, okay? Assume something on the left, assume something on the right, and you have a simple beam that you could analyze. If the assumptions are adequate, are close to the real situation, the results could be applied. If they are not, that means that the assumption do not hold, then the result will be quite different from the reality. For example, let's suppose that this stiffness here is similar to the stiffness of the vertical side. We could not assume that this is clamped. Do it, but the results are not going to be correct, because usually in this case, what is going to happen is that the deflection will be like this. Because we are assuming something incorrect. We assume that this is so strong, the vertical is so strong that even if it is connected here, they're not going to rotate. But if do rotate, then the assumption doesn't hold, and the result is going to be completely wrong. So if we could assume something, for example, on the side, you see that this is much stronger than this thing here. Definitely. Definitely. So in this case, what we could do is we can take this element and clamp it here. We'll go on. We have the loading. What we could do is we could assume or consider, for example, a simple support. Because if you try to move in this direction, okay, like this, if you try to move in this direction, it's very difficult that you compress too much this element, okay, so that it moves a quantifiable amount. But the rotation is a problem. So what we can do is we can include a corresponding torsional spring. So in this case, we could consider one single beam, clamp it at the bottom, simply supported with a torsional spring on the upper right, and then loading, which varies linearly because of the hydrostatic pressure. So this is something that we should start seeing, okay? It's kind of difficult to analyze the whole structure, but if we simplify, we could analyze a piece, and as a primary result, it could be useful. Let's take a break, people. Let's take a break. And when we return, we will go to see what the classification societies have to say for us. Isaac, would you please stop the recording?